Howdy, everyone. I'm here for day 10 of Advent of Code. This one was kind of a fun one. It did take me a little bit longer than the average one, and we'll talk about why that was. Most of it was just had to do with trying to optimize the solution. But we'll get into that in a second. Let's just talk about the problem and do an analysis of how I solved it. And some potential other ways. So day 10 is a pipe maze. Again, because we're doing the analysis, I won't go over the details, but the idea is you're going to be given a map that looks something like this. And each of these characters represent like a direction you can be going, or a direction a pipe goes, I should say. And here's the list of the different ways that they can go. The way to think about it is there's only two ways that you can go in a pipe. So for the vertical pipe, you can only go, like to exit it, you can only go north or south. For the horizontal pipe, you can only go east or west. So there's only two directions. And that was helpful, at least for me solving part one, is knowing like, if I'm in a pipe, I can either only go up or only go down or only go east or west. I can only go two directions, right? So if I've gone in it from one direction, I can only go out it from another direction. Okay. Then you have other places the dot is ground, meaning it's like definitely not part of the pipe. And S is your starting position. So you're going to do kind of like a graph traversal algorithm. And that's what it wants you to solve. So given this input, let's say the start position was right here, they want you to find like the loop in the input. And so what that looks like is if you start here and then you go here and then you go here and so on and so forth. Notice that there's like only valid positions, right? So if I enter here, I have to exit here. And if I enter here, I have to exit here, and then you can kind of traverse your day around. They use these ASCII characters, the 7, J, and L. I wasn't a big fan of those, so when you'll see me print out the solution in a minute. I actually use like the bars in UTF-8. They may be in the extended ASCII, but anyway, I use the bars to kind of actually make it look like a loop. Anyway, you'll see that in a second. So the idea, though, is you're trying to find that loop. From the start position, can you find the loop? And that basically just involves you saying, okay, can I go this way, that way, this, that, and you just follow the chains. The key there is, again, there's only one valid exit point once you've gone into it. And so the idea is if you're starting here and you know you need to go this way, you can say, this is my current position and my previous was here. You know you've gone into this dash from here, and so the only other valid way to go out is this way. And then you can do that kind of recursively, right? As you can say, okay, well, if I've gone this way, or if this is my current position and this is my previous position, I know I've used the input from this side, so I know I have to exit this side. That's just kind of the way to think about it. And given that, I made an assumption, which you kind of have to, it is the program says, hey, you have all this stuff. Here's what the input looks like. I can shrink it down a little bit so you can see here's what the actual graph. You can see there's a whole bunch of them. Here's the start point right here. Again, sorry, this is hard to see. It's a bit of an eye chart. But the idea is, can I traverse this thing to make a full loop? And again, because there's only an entry and an exit, it's really easy just to say, if I've gone in this side, I have to go out some other side, right? Based on the character I'm in. So an example of that, again, right here, if you look at this, if we zoom in a little bit and we look at like this position right here, if I'm currently here and I know I've come from here, I know I have to go this way. And that was basically the algorithm of the Find the Loop program. The actual question it asks you to solve is, once you've found the loop, what is the furthest distance from the start position in that loop, right? So if you're counting how many steps you've taken to get to that position, what is the furthest away you get. And that just happens to be like half the distance of the whole loop, which I'll show you in a second. So the way they describe it is if you start here, the furthest distance is obviously here, and it is 4 steps away. Again, though, another way to think about it is just if you do the whole loop is 8, you know that it's actually the furthest point is 4. You have to do some math because you're doing integer division, where you say if it's 9, then it's actually 8 plus 1. Or sorry, yeah, it's 9 divided by 2 plus 1, which gives you 5, right? So how do you solve that then? How did I go about solving the problem? Just some like boilerplate stuff. I made a point structure and implemented the add and subtract options. Those made it kind of easy for me to say like, oh, how do I know where I've come from and where I'm going? And along those same lines, I created this openings function, which basically says, give me a character, and whichever character is, I will return you like the 2 points that you can either exit or enter from, right? So if it's a bar, you can either enter or exit from 0, -1, meaning up above, or 0 and 1, meaning down below. And you just do that for all the different types. So then I can call this find loop function, which is a recursive function, and it essentially goes through and given the map, which is all of the points, which is a map of all of the points on the map and their character. So maybe I can just show you how I created that below in the main loop. I just loop through all of the lines, I enumerate them, and then I call flat map on looping through on for each of the lines, iterating and enumerating each of the characters and creating a map. So flat map, if you're not familiar, it basically takes an array and like unbounds the array, I guess is the way to think about it. So if you have a list of arrays, say you have an array 1, 2, 3 and an array 4, 5, 6, instead of having 2 arrays, you will now have one array that contains 1, 2, 3, 4, 5, 6. So that basically gives me all of the points and each of the characters at that point, and then I can just create a hash map of them. I felt like the hash map was the best way to describe like the map, because then I can really easily look up and say, hey, what is my position at this point? Without having to like do any plus or minus math or anything like that. I just know, hey, I need to get the next point in this list. Or sorry, I need to get like the point at this next position that I'm looking at. So given that, I just need to find the start position, and you can do that using the iter find, right? So I just go through this map and I search for the character S. So when I find the start position, I know I have it. Oh, I do iter find 0. I could do values here. I wonder if that will... I won't do it now because I think I have to fix some other stuff in here. But as opposed to just doing the one, this is my start position, and okay, so ignore that part. So this is my start position again, where I'm just finding the S in the map. So I'm just iteratively looking through this map for the S, and when I find it, it returns. So it short circuits for me. I don't have to worry about that part. But now once I found it, I need to know the next position. Well, it turns out if you look, I kind of cheated, which is not uncommon. If you look at your input, you can kind of know, you can say, oh, clearly at my current S position, I'll try and zoom in a little bit. At my current S position, I definitely can't go this way or this way because S would never connect to these this way, but it would connect to this 7 and J. So I know that my loop starting at the S is going up and down. And so for my solution, I just said, okay, if I'm going to find the loop, I know my next point is if I move downward. So my next point from the start is here. It is 1 point down. So then I can just call this find loop function, with the map, which contains all of the elements and their characters, or all of the points and their characters, and then my start position, which is the previous position, and the next position, which is the one down below it, and it will eventually spit out the total distance of the loop. And I'll show you how that works, okay? So again, the idea is given a map of points and their characters, and my previous point and my current point, I can increment the distance and add these points to my loop points if I need to. I could probably optimize this. I probably only need one of these because the distance is actually just the number of loop points in this hash set. So that would be another optimization now that I'm looking at it. But the idea is, given my current position and my previous position, can I recursively find the next position and increment these two values? So these are the two values that I'm kind of incrementing as I'm going through the recursion. So what is my sentinel case or end case? Obviously, if my current position is S, then I'm done, and I can do that calculation to find my distance. Again, so that's if it's an even number, I can just divide it. If it's an odd number, I have to divide it and add 1, right? Because the odd number actually means I'm at the end. Again, if the total distance is 8, the midpoint would be 4. If it was 9, it would actually be 5, right? Because I'd have 4 and 4 on each side, and then the 5th one in the middle, and so that's why that +1 is there. If I'm not at the S, though, I just get the openings for my next one, right? Or for my current position, and again, that's this function right here. So, say I'm at vertical bar, I know that my next points are my possible next points are either up or down, right? And so then I can compare I can find the one that isn't my previous position. So that's why I need the previous point, is I want to find the one that isn't my previous, right? So of these two positions, one of them is my previous point, and so I don't want to use that one, and I know it must be the next one. So that's what this logic does here, is it says, hey, now that I have those two possible inputs or outputs, I just want to find the one that's not the previous one that I went in. And once I've done that, then I can just add that to my list and call it recursively with an additional distance, right? So again, a high-level overview, if you look at the input right here, let's say I'm right here, I can check to see where I previously came from, which is right here, and so I know I need to go down here. So I add that to my list, I increment my distance, and then I call it recursively. So now I'm here, and I know I came from here, so I know my next position must be here. And again, the key is there's only two ways to go, so if I've only gone one way, I know that, or if I've come from one way, I know I can only go out the other way. And I can just increment and count that. So again, there's a couple optimizations here. Like I said, I probably just need to include the loop points here. I don't need a distance. Maybe at the end I'll try and improve that, and you guys can see me do that, and I'll do that other optimization. But that's it for part 1. So you can see part 1 was as simple as saying, create the map, the mapping of my points, and find my start point, find my next point after my start, which looking at the input made it clear that it was the next position down. And then I can just call this find loop function that will go through all those loops and do it for me. So how would this be an issue? It turns out that there's I don't know, some thousand number of points in the loop. I don't remember what it is, but 12,000. Because I'm doing this recursively, the number is a little bit large, but it turned to work out okay. If the input was extremely large, you'd probably have to unravel the loop. And again, so the way you do that and to possibly optimize it is you could do something along the lines of you'd still have your map and you just track your current previous distance or points, And then if you just like iteratively increment those based on the points, based on your next point and your previous and your current point would create that next iteration for you. I don't know how well I said that, but you could think about these being the variables in your for loop that you're incrementing until you get to the start again, and then you can break out of your for loop. Okay, so there's part one. Part two, what it's asking you to do is say, now that you've got your loop, I want you to find all of the points that are contained within your loop. And so here's a simple example. You can say like these two are inside, but these in here are not inside. Notice they can get out this way. So here's an example loop. These are stuck inside. They can never get outside. But like this one right here can travel through here to get out. They clarify that even more so is like it works in between these. Like notice this creates like this bounding box here leaves room for you to go in between these, right? So these, it can come out this way. So the question is, so these are still in, these are actually still out because they can travel through here to get out. And so they have like this really complicated example here where they say, here's something more. Can these ones get out? No, they can't, because if you kind of like travel through them, they get stuck, right? There's nowhere for them to go. But there are some, for example, that look like they might be inside, but they're not after you actually do the work. So this is just, again, you're saying like for each of the points that aren't in the loop, can you determine, or aren't a part of the loop, I should say, can you determine if it's inside the box, the bounding box, or if it's outside? So how does that look? If you look at it this way, it's very complicated, but I can show you, let me just run it again. And I will show you, this will spit out like a little graph. Oh, I'm going to have to zoom out, sorry. So it actually looks okay. So I did some drawing here. You can see my code to do the drawing of the map. But you can see these red lines, instead of like 7s and J's, I've turned them into the actual bars. And so you can see they create these little ways. And so when you ask a question is like, can these ones get out here? Well, yes, they can, because they can kind of traverse this area right here to get out of the box. Whereas, let's look for another one. I realize the yellow and greens are hard to differentiate, but like, for example, here's some green ones in here. If you look, they can't actually ever get out. Like, they can traverse through a bunch of stuff, but they always get stuck inside something. And what it's asking you, so it's just asking you to find all of the ones inside that bounding box. It reminded me of, for the job I currently have, one of the questions they initially asked me, this was 16 years ago because I've been working there for 16 years, but it said, can you implement the paint fill program like in MS Paint, where you like click a pixel and it fills in that area that's encompassed by like a circle or a square or something like that? It's kind of along those lines, right? Is like, given a point, can you tell if it's inside that circle, right? The fill program, you can just kind of recursively, dot here and then dot here, and you just keep dotting until you've dotted everything that's within the circle. This one's similar in that sense, is like you can kind of find your way out. It turns out, though, there's like a faster solution to it. And that is like it's called ray tracing, that the point at the current point. And Wikipedia actually explains it better. So I will include a link to this point in Polygon. I had remembered this from a previous advent of code, I think it was. Maybe it was a leak code problem, but one of these problems essentially asked you that same thing. And that's exactly what this program is asking, right? If you think about it, or part two is asking, is this point within this very convoluted polygon, right? So is it contained in that polygon? And that's what it's trying to ask you. So the way to think about it is this ray casting algorithm, which is the simplest. There are other algorithms that can be more precise. For our case, though, the ray casting algorithm was sufficient because there's no like potential for overlap or nearly overlap. But the way it works is, say your point is right here, the way you can tell that you are inside the algorithm is if as you're going through, is if you trace a ray. So if you trace a ray across it, so this one's tracing a horizontal array. If you just count the number of times you hit a line in that polygon. So here you have none, then you're 1, 2, 3, 4, 5, and at this point you've traced it 5 times. And so if it's odd, it means you're in. If it's even, you mean you're out, right? So if the point was right here, it would hit at 1, 2, and you know you'd hit 2 lines in the polygon, and so you now know you're outside of it. Here, again, just one more example. If you're tracing the line, you go 1, 2, 3. Oh, it's odd, so you know you're inside of it. Our problem is essentially this. It's a little bit tougher, though, because each of these lines represent something slightly, they represent both like a horizontal and a vertical. The 7, for example, actually represents, you can think about it as like, instead of this, it's represented like this as one thing, but it actually, on like a grid, it kind of represents 4 points. It represents like the empty, a line, and a line like that, right? Something like that. So the way that I like tried to solve that was, am I going horizontal to the well, maybe I should step back. The way that I solved it, the ray tracing, then, is I always counted up. So in a very simple example, like right here, if I'm checking this point, I always just count up and see how many I hit. So if I hit 1, 2, there's 2 of them, so I know I'm outside, right? If I'm right here and I count up, I hit 1, 2, 3, and now I know I'm up. Or now I know I'm in it, right? So that's how the ray tracing example works. The issue you get, though, is like this one right here, is you have 1, 2, 3. That would make you inside it. But that's because this one and this one are both facing the same direction, right? So imagine this one was actually facing this way on this line. That actually encloses it, right? If this was facing this way and this kind of went out further around like here, it's hard to see in this example, but the idea is now these don't actually get out, right? Because they like are encompassed over here. So you kind of have to track like how many times you're going this way and how many times you're going that way, and you pick like the smallest of those two will help you determine if you're actually inside or out. So I'm sorry if that was like a kind of a convoluted way to describe it, but again, the general algorithm is, can I do this ray tracing algorithm? And so what does that look like? Well, given a list of points and the ones that are inside the loop or are part of the loop, I can just find all the ones that I want to test, which I call dots, and that happens to be if they're a dot or they're not in my loop. It's actually probably easier to just say if they're not in my loop. But the idea is now I have every single position in the map that's not a part of the loop, and then I can just iterate through them and see how many looking up, right? So I'm going to traverse up. So I say px are equal to dot x, and the py is equal to the dot y. So get all of the ones that are going up that are lefts and count those. And then get all the ones that are going up that are rights and count those as well, right? So given a specific point, like right here, I would get this one, and this one. The dash happens to be both left and right, so I count them in both places. But like this one right here, I would get a left, and a right, right? So I get both of them here. Now, given those two things, so I get lefts and I get rights, I just, based on the minimum, I do a modulus 2 and get the remainder. And so I say, this is just asking, is it odd or even? And if it happens to be odd, I know I'm inside. Otherwise, I'm not. So I don't have to put it in my list of inside points. So this turned out to be really slow. If you look again at my cargo run, it takes about 3 seconds to run. And this is where I actually spent most of my time trying to optimize it, was it didn't feel like, it felt like you could solve it faster. And so this was, in my mind, this was a simple way to describe the algorithm, maybe is the way to say. I basically say, find all the points that aren't a part of the loop, and for each of them, count the number of lefts and rights that are above it inside the loop, or that are a part of the loop, and then I can just see if it's inside it. But I'm doing that for every point. And if you think about it, the way that I came to a faster solution was I said, hey, if I'm, let's just take this whole column right here, for example. I have to test this one. I have to test this one, this one, this one, and this one. Well, it turns out if I'm looking up, if I've already calculated the number of ups right here, I can if I've maintained that state of the number of times I've seen horizontals, this one is not any different than this one. Does that make sense? And this one is just the values that I had used from the previous value plus the additional one right here, right? The idea is, if I'm looking at a single column, if I'm traversing down the column, the counts of lefts and rights that I've got above it are just the same plus the one that I'm currently looking at right now. So I don't have to like recalculate all these counts as I'm looping through these, because I've already calculated them before. You can think of it as a little bit like a memoization technique. So it's not quite the same, but it is along those lines of, hey, I've already calculated all this stuff above for this one. Why do I have to recalculate it for that one? And so my in-loop faster function is the one that does that. So instead of finding all the dots, I'm just going to do a for loop for the X and Y axes, right? So for each column, I'm going to look at each value in that column, and I'm going to track the left and rights in that current column. So if I'm part of the loop, I want to see how many lefts and rights I need to increment based on the current value at the position I'm at. If I'm not in the loop, I can use these values that I've been tracking from previous iterations to determine if I'm inside or outside the point. And that drastically reduces the number of calculations, right? So this one, I don't have to do really any new calculations because I've already counted them when I did this one. This one only differs from this one in this additional calculation right here, right? Is now I have a horizontal, so I've added a left and right to each one. And that's how this one turns out to be faster than this one for solving it. So again, when you look at the solution, I do get the right answer both ways, but when the difference is the naive solution, where for each point I'm like iterating, I'm checking all of the ups, the new solution only takes 7 milliseconds because I only have to calculate any additional differences that happen between like this position and this position. The only differences are like these two right here, right? Okay, so that was part 2 of day 10. How do I feel overall? The part 1 was not really that hard. It did take a little bit of thinking and reasoning to say, at least for me, the key was, there's only 2 ways you can enter and exit each of these pipes. And so I can just check to see where I've come from, and now I know where I need to go next. So that kind of made it relatively trivial because I can just now I can just draw the map and find all of the loops in there. Part 2 was a little bit more complex, but the key was And again, if maybe you didn't know about the point and polygon, but you could potentially search if you had been Googling around, you probably could have found this relatively easily. Although I would love to hear your input, like if you would have ever gotten there, or maybe you found another way to solve it. I'd had to think a minute if there's another way to solve it. This just happened to be mine because I know that I had seen this stuff before from a previous problem, so it came up. But you might be able to Google and say, oh, how do I find if a point is contained within a box, right? Point within a box. Or like a check if a point is when a... Oh, how... I don't... Maybe you wouldn't get there. Check if a point lies inside a rectangle. These are like very... You'd have to know that it probably was a polygon. Check if a point is inside a polygon. Yeah, you'd have to know that this actually produces a polygon. Right? So this itself is a polygon. But I think most people could probably get there, maybe with just like that hint of saying, oh, think of this as a polygon, if you haven't seen a problem like this before. That being said, I'd like to see, I'd like to get your input on that. Maybe just because I had that previous knowledge of a problem that simplified this solution for me. I did have to iterate on it a little bit though. So like, again, I'm showing you like my final solution. But I had this original solution that was relatively slow, and I had to discover that the left and rights actually accounted for it. Like when I first solved it, I just assumed it was any time you hit a horizontal point, and but that doesn't account for the key that got me there was this part right here, where it says there doesn't even need to be a full tile path for the outside tiles. They can squeeze between the pipes, right? Like this idea being, okay, well, there's some bounding box here, even though it looks like this is part of the path and there's no way to escape, because these create like an exit way in between them. You have to like calculate the lefts versus the rights. That's how I got to it, at least. Maybe there's some other way to get to it where you could say like, oh, I'm just going to expand all of these values and like do something in between them. You could do like, if you doubled all of, I don't know if that would work. It'd be something to think about, but like imagine scaling this out to like double, and now you can determine if these are all in there because there would now be a space in there. That's something to think about. Anyway, if you solved it that way, that would be cool. I'd love to see your solution. But that's where it is. And again, the faster way was just recognizing that, oh, I can actually just count down, or I can reuse the values from here for the values from here. So there you go. That's my analysis. Overall, the problem was definitely harder than previous days. Like you definitely had to think about the bounding boxes and understanding the points and polygons. So I can see those being harder. But if you actually like look at the finalized solutions, it's not like a substantial amount of code. I think that's something interesting about programming is sometimes the harder solutions tend out to not actually be a lot of code. It's just the way you've like reasoned around creating that code. Like if you didn't do it this way, there's a potential for you to try and check lots of edge cases, right? Like you could say, oh, my solution is going to try and like do a flood fill and see if I can ever like get out to any of the edges of the map. And if I do that, then I know I've solved it. That one would technically work too. It might be a lot more code though. So anyway, there you go. I had a lot of fun doing it. I did a little bit last night when the solution version. I got part 1 last night, but was too tired to even think about part 2, and so that's why I'm just doing an analysis. It's kind of a 2-part thing. There you go. This is my solution. Hope y'all have fun doing the advent of code. And again, I appreciate all the input. Love to hear how you solved it. Love to get comments. I'll happily answer any questions. I'm sure there's some parts I didn't explain very well, so if something doesn't make sense, just let me know. I'll happily try and explain it further. Okay, talk to y'all later.